So today we will be discussing about the algorithm Sieve of Eratosthenes. It is a very ancient algorithm that was designed back in 3 BCE to find a prime numbers between a given range. One of the most fascinating things about this algorithm is that it is still relevant today, and it is widely used to find prime numbers in a given range, even though it was created, it was invented back when computer wasn't even a thing. So what kind of principles, the underlying principles for the algorithm, that make it so efficient and widely used even after centuries, right? So before actually jumping on to the algorithm, we should be discussing about the concept of space and time, right? So an algorithm has space and time complexity, right? And the trade-off between them is simply that if we have let's say an algorithm that have a time complexity huge, then we can trade off that time complexity by caching in some of the work in some memory, right? So we are trading off our time with space, and we can do that same. If it's taking very extra space, then we can trade off memory with real time operations. So here we have to reach an equilibrium such that space and time complexities are kept to the minimum, right? So this is an approach when we think of actually moving from the brute force approach to a very efficient algorithmic approach, right? So the problem statement is for a given input n, write all the prime numbers from 1 to n. And when we think of its brute force, the brute force for this algorithm, the time complexity is quadratic in nature, right? And quadratic time complexities are not really efficient. So we have to, think of an optimized way to actually, make finding prime numbers from 1 to n really fast, right? So before obviously optimizing, we have to think of the actual brute force approach and how we can optimize it, right? So in brute force, what we are doing is we're traversing from 1 to n, and then we are checking if that number is prime or not. It returns true, then we insert it into the list. If it returns false, we don't, right? So is there something that is redundant that we can trade off, or is there any more good approach so that we can reduce its time complexity? Well, the idea of Eratosthenes back in 3 BCE was to think that what if we create, a table of cells representing 1 to n, then mark off all the composite numbers by marking off all the multiples of the prime numbers as false, such that we don't have to actually design the is prime function, right? So this principle can be converted into a famous algorithm, Sieve of Eratosthenes, and we will look it in a more deeper way here. So when we are traversing from 1 to n, and then we are sending that number to is prime function, what is prime function is doing is that it is also traversing from 1 to x and finding that if it has a factor that or not, right? In prime numbers, if the number has a factor other than the number itself and 1, then it's a prime number. So let's suppose we send 6 to the is prime function. So what is prime function is doing, it is traversing from 1 to 6, and if it finds a factor, let's suppose 2, 3, 4, or 5, then we know that 6 is not a prime number. And in 6, 2 is a factor, right? So 6 is not a prime number. But we've already traversed from 1 to 6 before, so why will we be doing it again? This is a redundant work, so we can cache it into a memory, right? And this is the basic approach, right? So in this animation we start from 2, and then we mark off all the multiples as false, right? Then we will go to the next prime number and mark it all off at false. Then we go to 5. So when we reach 4, it is marked already false, so we know that it is not a prime number. So we don't have to mark any multiples of 4 as false because it has already been marked by 2, right? So in this way we are actually listing up prime numbers, and before actually arriving to the number we actually know its nature, if it is prime or composite. In that way we have reduced our time complexity from a quadratic to n log n log n time complexity, which is really efficient. It is actually equal to just linear time, if you think about it, right? So we should jump to the code, right? And this is a very simple code, very simple implementation of Sieve of Eratosthenes. There are many, optimizations we can do, and you can find it on the CPB algorithm site. They have a very great article. But here we will go very beginner friendly. All we are doing is we are taking an input n, and we are, putting it in the function Sieve of Eratosthenes, which is giving us a list of prime numbers which we are printing out, right? So what kind of magic is happening in Sieve of Eratosthenes? Well, first of all, we are creating an array is prime, which, tells us if the number is prime or not. And this is a array that we need to return prime. This is empty for now. This is a boundary cases. We can handle it anyhow, but I have done it here, so it is very clear that 0 and 1 are obviously false, right? And obviously we don't want to traverse through the multiples of 1, because then every is a composite number. Then we traverse through this loop, right? And if the number is prime when we are traversing that number, and that number is prime, then we will mark off all its multiples as false. So the first number that we will encounter is 2, because 0 and 1 are already marked false. So the first number which is true is 2, and then we will mark all the multiples of 2 as false. One optimization I've done in this simple code is I square. Why we are starting from I square? Well, I think I got a very simple explanation. Suppose we have to mark off all the multiples of 6, right? And 30 is a multiple of 6. So we can break 30 into 6 into 5. But we don't have to do it again, because 5 comes before 6. So we have already marked 30 as a multiple of 5. So we don't need to do this with 6 again. So we can start from 36, which is actually 6 square, right? So this is a little optimization we can do. And like we promised, we are marking off all the composite numbers as false, as we have found the multiple. And then at the end, when we have marked all of its multiple as false, then we are pushing it into our prime list. And after we have done all the work, we are returning this prime list, and we are printing it. And that is how simply it works. So let's see how it works, right? So I'm running this code, Sieve of Eratosthenes. Let's put a number 1600, and we can see that it has given us the list of numbers between 1 and 1600 which are prime. So this is Sieve of Eratosthenes, and it's a very simple algorithm, but I think it lays the basic foundation of how we can optimize algorithms by figuring out the redundant work and caching it in some form of memory.